Bueno, si está Joseph, ya sois dos.
Luego vienen los experimentales, que son otros dos, que son 4, pero se van avanzando con el dedo de la mano. Esto es protección, no prepares mucho para lo que tengas hecho ya más o menos.
Sí, esto lo tengo hecho porque...
No te preocupes mucho.
Esto es lo que voy a contar en Kent el próximo día, en la Universidad de Kent.
Bueno, mira, te sirve para nada, ¿eh? No es una pérdida de tiempo.
No, además todo esto es algo que estamos analizando y pensando bien cómo contarlo todo en un par de papers que tenemos que sacar ahora.
¿Qué significa hypervelocity?
Pues muy alta
Velocidades
velocidad,
muy altas.
pero sí, luego explicaré a qué me refiero con hyper.
Vale.
Pues podríamos decir high velocity o esto llega a ser hypervelocity.
Suena como
velocidad absurda, ¿no? O sea, de las películas de ciencia ficción.
Un rampante y los de Bangor usan un dragón.
Sí, es el...
He querido meter un dragón aquí mitológico.
Es un poco friki ese logo, es un poco dragones y
Juego de
mazmorras,
Tronos,
¿no? Una cosa así. Pero bueno.
Así como un león no está mal en la heráldica. También para universidades tampoco pega, ¿eh? El compás sí, pero para...
El Chef Technical University.
¿Eh?
Bueno. Sí, el logo de CPU.
Sí, de la Czech. Venga, University in Prague, que tampoco...
SCK CENES, y esta otra, SCK CENES, donde está Giovanni Boni, que quizá te suene su nombre. Este y su grupo, por lo menos en tiempos, desarrollaron potenciales para distintos metales y todo esto.
No, yo no estoy muy puesto en
Entonces, bueno,
potenciales.
O sea, para alguien que sepa de algo que está en el mundo de la dinámica molecular clásica y todo esto, pues le puede sonar el nombre. Entonces resulta, porque todo el mundo es un pañuelo, que Prasan, mi estudiante, trabajó con ellos en Bélgica antes de ir a Praga. Entonces, bueno, pues le dijimos, venga, si quieres que Giovanni nos eche una mano con esto y tal.
Ay, no hemos preguntado nada de necesita. Bueno, el micrófono te pilla, me han dicho.
Ha dicho que funciona.
No es este. Son micrófonos que hay por ahí.
¿Vale? Se ha dicho que está en el techo.
Sí, están por ahí ocultos. O sea, debe ser, creo que la placa entera. Sí, algo así. O sea, hay micrófonos por todo lado.
Que hay 3 participantes.
¿Cuánto?
3.
Sí, 2. Yo, otro y...
Sí. No sé si el otro será el técnico de... Pero bueno.
Ahí.
Minutos, 40 minutos de la charla, ¿no? De las preguntas. Mi charla, 40 minutos más preguntas.
Sí, más preguntas. Por lo que te pregunten, pues se va a arreglar un poco. O sea.
Tengo varias cosas. O sea, podría hablar mucho rato, pero bueno, voy a ir. No.
Bien, ¿tú?
Bien. Tú trabajas con Andrés Vega, ¿no?
Sí, fue mi director de tesis, sí. Mi director de tesis fue.
Que vino aquí a darnos a una tesis. Me dijo que dónde estabas, pero pasamos por buscar que no estabas.
¿Cuándo? ¿Hace poco?
Fue hace 10 días, en marzo, desde marzo o principios de mayo, cosas así.
Pues no me dijo nada.
¿Eh?
No me dijo nada, sí, ¿no?
No, porque
No me ha
supongo que
gustado.
sería. Bueno, esto de las tesis ya sabes, va a ser
Sí.
y bueno, desde las 8 de la tarde tenemos al día siguiente de la tesis, comida y esto es la comida de vuelta. ¿No?
Hace mucho que no voy por allí, la verdad. Hace mucho que no me paso por allí y les veo. Les visito ahí en Valladolid.
No sé qué tal les irá, lo que se puede, pero estuvo aquí que estuvo trabajando con ellos, con los you know him?
Sí.
Alberto, ya, que introduce, no, sí, el que estuvo aquí fue Rodrigo, que es un equipo de la tesis también con Andrés, pero hoy aquí de Pozo, a soltar de abrir. Me salió una de estas de como 3, 4 años para dar clase. Que supongo que si lo hace bien, pues lo mismo como en la titular, pero veremos. Tendrá que trabajar ahora. No tener ni una semana.
Así.
No tiene otro trabajo, no sabe. Yo trabajo allí, pago allí, sí. No sé. ¿Empezamos a estar o we wait for Martina is coming o bien o no?
I think she has a meeting with
She's
the
got a meeting, yes. Okay. Maybe you can start. Well, we can start with the meeting, with the talk. It's a pleasure to introduce you Dr. Alberto Fraile. He made the PhD thesis in Madrid, in the Institute of Nuclear Fusion, under the direction of Professor Perlado, Manuel Perlado, and then he has moved a little bit around Europe, Crete, Prague, and Bangor, which is his actual affiliation in nuclear things, and he's going to talk a little bit about some nuclear materials using nuclear fusion, and that now is so interesting in the press and so on. So please, the floor is yours. You have around 40 minutes or so.
Thank you, Andrés. Thank you for the nice introduction. So, yeah, my name is Alberto Fraile. I did this work recently in collaboration with Prasanthi Wedi, who is my student in Prague, Czech Technical University, and in collaboration with Giovanni Boni in Belgium and Thomas Polser, who is in Prague. And the title is Hypervelocity Impacts from a molecular point, from atomistic point of view. So I will explain now. The motivation of this work is nuclear technology in magnetic confinement nuclear reactors, tokamaks. You have that sometimes dust goes back to the wall at very high velocity. So this was discussed for some years. The high velocity was 5 kilometers per second, 7 kilometers per second. More or less now the consensus is that it's about 5, the limit. But in general, it's very high velocity, and this creates this kind of craters that we see here. This is an actual crater in a tokamak, as in the plasma-facing material that is generally tungsten. So tungsten is the main candidate for plasma-facing materials in ITER and beyond. So this is an example of a crater in tungsten in a dedicated experiment. So it's an impact of tungsten particles in tungsten. And the one on the right is the simulation using MD. So of course, we are not in the same scale. Here, the craters are in the size is microns, and we are in this nanometer scale. but we are in the same scale if we look at the kinetic energies. So I will talk a little bit about the methods and some benchmark. Then I will present some results in single crystals. A little bit about polycrystal, because real life you don't use single crystals in experiments and everything. And what about if you have more complicated targets, like when you have helium bubbles and things like that inside. So in the simulations, we have a target that is just a box full of atoms like this size more or less 600 times 600 times 400 cubic angstroms or something like that, up to 200 million atoms in the largest simulations that we did. We changed the size according to the kinetic energy of the impactor. For very high velocity, we use very big targets. The projectiles were spheres of 4 nanometers, 8 and 10 nanometers, comprising 2,000, 17,000, and 35,000 atoms approx. And the velocities were from 1 to 12 kilometers per second for the small impactors, reaching kinetic energies of 312 kiloelectron volts in the highest ones. The time step has to be short, 0.1 femtoseconds, to conserve the energy in the simulation. And the total simulation time is 100 picoseconds. In some cases, we double check 200 picoseconds to see if everything is kind of stable and equilibrated, let's say. So this is very heavy simulations and computationally very expensive. So every simulation was about 50,000 CPU hours. Very packed. Okay, and then we did it with 2 interatomic potentials, what we call Marinica and Olson. And in both cases, the potentials must be corrected with this zeta BL correction. That means that you have to make them a little bit more repulsive in the short distances. Otherwise, the impactor for the high velocities just goes through the target like if the target is nothing. So just to benchmark the potentials, we did a few simulations and tests. And this is, for example, the equation of state. So we present here the volume versus the pressure. And we compare the simulations with Marinica and Olson compared to the theoretical work presented in this paper. And in both cases, the agreement is fair. But the reason to use 2 potentials is also that it's tricky to know when the potential will be good or not for these kind of simulations. We want to model properly the target, the material itself. So we want to have a potential that gives reasonable mechanical properties of the target. But also the thermodynamics is important. So for example, here we see that with these 2 potentials, we have more or less the melting, that is this jump in enthalpy, in the same point, more or less, 5,000. Okay, it's overestimated because this is always the case in general, but it's more or less the same, the melting. But what is not the same is the recrystallization when you do this kind of cycle. So the 2 potentials are similar and different depending on what we look. Also, they are different if we look at the jump in volume here at melting. Okay, so well, we can compare this with the experiment and everything and know more about which potential looks better. We can calculate the structure of the liquid. In both cases, it's pretty much the same. Here is the table with elastic constants, bulk modulus, etc., compared to the experiment. They are similar in the solid phase, let's say, but melting point, latent heat at melting, and different properties like that are not so similar in both cases. So I will discuss later when this is important. Then we can do the simulations, and we can see, for example, here, this is the impact. The color code is the kinetic energy of the atoms. So what we can see is how, for example, the kinetic energy of the atoms of the projectile are at very high kinetic energies at short times, and then this histogram moves to the left, meaning that they stop in in these 100 picoseconds, they are all at low kinetic energy below melting point. And with the two potentials, these kind of histograms are similar. So it would mean that the thermal conductivity more or less is the same in both, with both potentials. And then what we call hypervelocity impacts, because the title can be why hyper. We can talk about low velocity impacts when we are below 500 meters per second, more or less. Then we talk of high velocity impacts above 500 meters per second and below 4,000, more or less. And this number, 4,000, can be calculated like the square root of the compressibility divided by the density, or can be just taken as the velocity of sound in the material. So more or less 4 kilometers, 5 kilometers is the limit or the threshold between high velocity and hypervelocity. And then up to what velocity we can really go with classical molecular dynamics. In this paper, they analyze the contributions and the thermodynamics of the hypervelocity impacts in different metals. So for tungsten, in this graph, this is the total energy, the red one, and then this one, the light blue, is the elastic contribution in impact, and then the other one is the electronic, this one. So above 12 kilometers, more or less, we have that the electronic contribution is larger than is higher than the elastic. So we cannot ignore the electronic excitation that you have in the target above very high velocities. So that's why we went up to 12 kilometers, and even less will be safer. And of course, if we do just 100 meters per second, it's not something so exciting, or it's not. We don't have that kind of excitations and things. In that case, just the impactor touches the surface and then goes up, bounces back. So this is expected, is also observed experimentally, but we didn't study much this very low velocity. When we do 500 meters per second, for example, then we have that the impactor is attached to the surface. So this is the shape that it has. It was spherical before. The volume in the two cases is about the same, volume divided by the volume before the impact. So the shape is the same, but what is not so the same is the amount of atoms still in the VCC phase. So in this case, we have that more atoms are disordered and amorphous after the impact. So I deleted here all the atoms that are not in VCC, okay? And these green and red are other phases, but it's not really phase. I mean, when you do this common neighbor analysis.
How are the atoms in the target and the particle modeled? Because you're saying that there's an electronic part and then there's some other part. So how is it modeled exactly?
Well, okay, the electronic properties of the atoms, let's say, are just all in the potential. Is the potential that I said are unique, and also is just names, are embedded atom method potentials. So it's the classic atom, is the classic potential for metals in classical molecular dynamics. Mm-hmm. It's an interatomic potential that describes all this, the interaction between atoms. Yes, thanks. So yeah, the two potentials here are showing some differences in the amount of recrystallization and even in the low velocity regime. Then this is a simulation of what we see when we have high velocity impact. Okay, so you see that the tungsten is like water. This is just 3.5 meters per second, kilometers per second. And so we have this crater, we have the rim, we have a lot of atoms scattered, like individual atoms and also clusters, and we have all these dislocations in the target. So the target is, the atoms in the target are removed to observe the dislocations. So we can calculate the total dislocation length in the crater, in the target, I mean. So it goes up, and about 20 picoseconds, we have starts the recombination. So all the dislocations will start combining, and finally we have some dislocation forest like this. So there are a lot of things that we could talk about this. And we can calculate the volume of the crater and much more. The basic thing is this, the volume of the crater. That is what we can compare to with experiments. So the volume is expected to be linear with the kinetic energy, and it is, although it has kind of apparent deviation for the very high velocity, but it's basically linear, so can be fitted with this simple formula. So the term here, the slope, it's called cratering efficiency. And we have these two values for the two potentials. And it looks that the ratio between these two slopes is about the ratio between the two latent heat of melting of the two potentials. So with this potential, the latent heat at melting is lower. So you need less energy to melt the tungsten according with this potential. So you have a bigger crater with the same kinetic energy. And it's not exactly like that, but it seems that it's an important contribution. Then if we compare to the experiments, here we have all our MD results, and here the experiment. It looks good to me, but okay, someone can say that you have a big gap here, a lot of orders of magnitude, and it's true, because the kinetic energy is the same. I mean, the velocity is the same, but not the kinetic energy because of the size of the impact of the particles. It's true, so you can say, okay, you have like a point here and a point here, and then you can pass a line, fine. But it's true. If we divide the volume by the volume of the impactor or the projectile, so we can put this in without dimensions, we have all the experiments and the simulations in the same curve and in the same graph. And it can be fitted with this model. I forgot to put a reference, but it's one of the theoretical models for this kind of craters. So the volume looks fine compared to the experiment. The experiment is tungsten on tungsten also. So I mean, we are not comparing to random experiment of some other material. So it's the real one. And if we look at the depth of the crater, also divided by the diameter of the projectile, to put everything in without constant, without units, again, we have like a good fit and a good match with the experiments and the simulations. So we have more points because we can go up to whatever we want in the simulation. The experiment, they went up just to 4.5 kilometers per second. And again, the simulations are fitted with this model quite well. So it's just a model that will, it has only the density of the projectile in this case, and two parameters here, and B is the velocity. And to finish with this, we can also calculate the diameter of the crater divided by the diameter of the projectile. And again, we have this curve. The experiment and the simulation, everything is fine and can be fitted also with another model. So everything looks quite good to me. And it has to be said also that when you are doing something very small, in this case, nanometers, there are things that are size dependent. For example, the melting point of these nanoparticles. In a nanoparticle like this big, the melting point is 0.8, the melting point of the bulk. In a nanoparticle like this, big enough, the melting point is almost the melting point of the bulk modulus, of the bulk material. So this is also something to consider when comparing these results. So this is what I was saying before, the melting point divided by the melting point of the bulk material has this depression here. Then for big enough particles, it goes just to 1, the ratio. And there are different models like that. So So it's expected also to have some disagreement in the very low, when you use very small nanoparticles as impactors. And then about the total dislocation length in the target and everything, this is the movie I saw before. We could analyze a lot of things. One of the important things is that is size dependent. So what I'm showing here is two curves. Total dislocation length goes up and then down. As I said, we have recombination. But in this case, these full symbols are 3 kilometers per second, and these empty symbols are 8 kilometers per second. So velocity is different, but because the size of the projectile is different, the kinetic energy is the same. Okay, so being the kinetic energy the same, we have different result. Okay, so it's because the size is size dependent. So this will be clear now. So that's why when we plot versus the kinetic energy, the results, we have two sets of points. The results using the small projectile, the results using the big projectile, for example. And in this case, the results are not so potential dependent. So you can see here both symbols are more or less in the same curve. Before it was potential dependent, but depends on the size. And now the ratio between these two, it's about 4, I thought, because I thought it would be matter of the size of the two impactors that has this ratio, but it's not really 4. So this is being analyzed. And something.
What's the total displacement length here?
Sorry?
What's the total displacement length?
No, not displacement, it's dislocation. So if you count all the length of all these segments here, so it's total dislocation length. Yes. So this is really a lot of work ahead. We have to analyze the hardening effect of these dislocations in the target, and we could also analyze what we have consecutive impacts and all that. And much more. We can also analyze the differences between different orientations. So the target, I didn't say it, I think, but the target in all the results that I presented is this 100 orientation parallel to the impact. So in this case, we have this kind of dislocation forest. For this orientation, in these cases, the velocity is the same and all that. We have a different one. In this one, we have a different one. So this is 30 picoseconds. In 100 picoseconds, that everything stops. We have at the end something different, and we could analyze this, and we are doing it a lot, but I will skip that part. So this is summarizing what I was saying, but we have different plastic deformation, and we have like different total dislocation length. Also, we can look at the craters from the top, and we can see different symmetries of the crater and the rim. So in this case, it looks like a square. Here it has this symmetry, and this one, with some imagination, it's kind of hexagon. And then, of course, we can calculate everything that I talked before, like the depth of the crater and the diameter of the crater and everything. But the difference is not that big. So I cannot see here some clear trend or anything. The same for the volume or the ratio between the depth and the diameter. So it's maybe a more boring part. We can also change the angle of the impact. So of course, not always the impacts will be perpendicular to the surface, but can be more like with some angle like this. And then of course, we will have some crater that has some symmetry. Not only the crater will be not non-circular and everything, but also the dislocations are different. So we have this kind of wings. This is seen from the top. So the impact was like this. and then we have these dislocations going like that, and then ending like that. And the crater in a normal impact in perpendicular has the expected symmetry, but when we have, for example, this 60 degrees of angle, then we will have something that will be elliptical, and we can plot that. The ratio between those two axes is called circularity. So it's 1 when the impact is perpendicular, and then goes to 0 point something, and so it goes like that. And our end results are all these circles here, and there are a lot of experimental results, but in different in aluminium, so not in tungsten in this case. But this is expected to be for all metals, so that's a matter really there. Although it changes, but this is expected, and well, okay. We have a good agreement also with other experiments. And then very important is the effect of the temperature, but this is quite tricky. And I couldn't find yet a model that describes this in metals. So we can plot the volume of the crater for these velocities versus temperature. And the higher the temperature, the higher the volume of the crater. So the material is softer, let's say, so the crater is bigger. And it can be fitted more or less. Maybe 3000 was too much, and those points are, well, maybe we should ignore that. Can be fitted to the compressibility to the power of 8, but I don't have a reason for that. So this is something that I'm doing some numerology. So this is just to show that it goes up, and we don't know yet how to fit or how to explain this properly. Of course, one can invent a more complicated model, like, for example, compressibility times the solidification time to plot something. And then we don't need a 8 in the compressibility. We can be just compressibility times the solidification time fits quite well the results. Solidification time depends on different parameters like the density, thermal conductivity, heat capacity, and the temperature. So this is something that well, we are working on it, but couldn't find good models for this. So this is something that is quite unexplored, and is very important because simulations, we did it at 300K, but the material in the tokamak, for example, won't be at 300K. So
with the temperature, you refer to the temperature of the particles or also to your wall?
The temperature of the target.
Target only.
Yeah, before the simulation, I mean, then after the impact.
And the particle itself, you put it, you have
yeah, we could do that as well. I mean, in all the simulations, the target and the particle are at the same temperature, 300K. Then you do the impact, and then in these cases, when we talk about temperature here, is the temperature of the target, what is different. But we could do the reverse, that's true.
What's the temperature of the wall in the actual tokamak?
Yeah, it's supposed to be higher, probably, but less than 1000, I think. So in general, for tungsten, is low. I mean, tungsten is very hard to melt.
So in the real tokamak, the temperatures are lower. It's on the low side of what you have.
Yeah, we did. That's why I was saying that maybe 3000 is really too much. So maybe we have to just analyze properly this part of the graph and everything. So maybe 3000 is really too high, and we don't care. So yeah. And then to go also to more realistic targets, we can also think about polycrystals. So we can make a target that is polycrystalline. We use something called Atomistic. I don't know if you heard about this code. So you can define you can say the number of atoms the number of crystals that you want in the polycrystal, and you have something with random orientations and everything. Well, and in that case, the crater, as you see here, won't be semi-spherical. It will have some asymmetry due to the grain boundaries, for example, here, and you can have much more. You can have also cracks like this, so it's much more complicated. But in general, doing a little bit of a systematic thing, we have now 3 different samples with this average grain size, so this number of grains. When you decrease the number of grains, the average, you have a lot of grains. When you make them big, you have few. And we did, again, for velocities. And if you look at the crater from the top, you see differences. And for example, here you see cracks in this crystal, and this is more clear when you do it at 4 kilometers per second. So, but in general, well, it looks like the same, the semicircular and everything. The thing is that if the kinetic energy is not that high, well, you are only touching probably 2 or 3 nanocrystals, so the rest are not really affected, but you see differences. For example, here you see that the crater has this asymmetry in this cut, so it's not semicircular like before. It depends on how is the polycrystal. So one should do a lot of simulations to have really statistics and everything, but right now we have some results, and the single crystal case is the blue squares. Polycrystal with a lot of nanocrystals, it's more or less the same, although here it presents higher values for the volume of the crater, and for a small number of crystals, so big nanocrystals, we have lower values for the volume. So we are analyzing this, repeating more simulations to have this clear, because maybe depends. You can do another sample with 5 nanocrystals, but these nanocrystals can be different orientations and everything, so the result can be maybe very different. So just to finish, we can do more, and we can also add helium bubbles, for example, in the target, because in the material you will have helium and tritium, and you can have different things in the real tokamak along the time. So if you have helium bubbles, this is the shockwave that is being generated here after the impact, and then you have all the dislocations generated here. So the interaction of the dislocations with the helium bubbles and everything is quite complex. And then the pressure and the shockwave will compress the helium bubbles and then can coalesce also depending on the distance. And also, for example, this one here that was close to the surface can just break and the helium will go up. So, well, this is something for another paper, because you can here analyze a lot of things, and you need also to do a lot of simulations to have statistics on everything that is happening here. That you can imagine that is a lot of things are happening there. But in general, what we saw is that about 10% is the change when you have a helium bubble, basically around the impact. So it's not that big the difference. And everything was published in Nuclear Fusion, and they put this figure that was in our paper in the cover, so it was nice. A couple of papers are now to be published, so this is more or less what I presented. The main point is that we believe that the simulations are very realistic, despite of all the approximations that you always have there, because they match quite well now the experiments that they did very recently. And just to finish, I would like to say a few more things that maybe for you doing more electronic properties and things like that could be interesting. So we did it with tungsten, but it could be done with another metal. For example, aluminum will be it will be easier to melt and do. So you will have bigger craters, and you will have more melting and vaporization and everything. So the point is that when you have high velocity or velocity that is high enough, the energy of the projectile is not just spent creating the crater, but also you will create a plasma and some electromagnetic pulse as well. So there is some radio frequency emitted. So there are some experiments on this, but I didn't see good simulations on this. So this is something that I think that maybe I will do someday. Yes, maybe. So this is another picture of in the same paper, I think. So there are a few simulations, but not atomistic simulations. This is more like hydrodynamic codes, more than atomistic simulations, but could be done with potentials not embedded atom, but reacts force field, for example, that are potentials that take into account the charge. And finally, another thing that could be maybe interesting someday is to study the magnetism after the impact. So this is something that it's important in geology or astrobiology, or astrophysics. Well, in geology, in planetary science. I mean, I didn't want to say astrology. So magnetism can be also studied now using molecular dynamics. So it's called spin lattice molecular dynamics or spin dynamics molecular dynamics. And these are two examples of papers recently published by Pablo Nieves and I know Pablo Nieves, Sergio Garapan, Dominique Legout. I know them, and in this one we did a paper together. So this is something that is quite recent and is nice because now you can also add magnetism in atomistic simulations. So it's something that maybe someday could be considered, doing some high velocity impacts in some iron or nickel or something, and study what can you learn from that. And with that, thank you for your attention, and thank you to my colleagues and collaborators.
Thank you very much for the presentation. Are there any questions, comments? Yes.
The question. So when you have your impact on a single crystal, at the end, what you show in the image is not symmetric. Why is that? I mean, there was some crater somewhere. Why? I mean, in the calculation, I would believe you get out something completely symmetric then. Or the molecule, if there's some chaos theory or something like that, I would understand. But I mean,
where exactly?
Now here is Here, for example, just at the next one on the left-hand side. So you have the impact's completely perpendicular. Why you have then craters there inside?
Do you mean?
Yes, these guys.
This? Well, here the color code is the position of the atoms from this distance. So it's just to see the ring. You have this symmetry because the target has a symmetry as well. So this is 1,0,0,8.
Yes.
So it has this symmetry. Why you have some cracks or something in some direction? Well, this is not really deep. I mean, it's just in another simulation will be a little bit different. So it's how the tungsten melted and recrystallized here. So it has some arbitrariness, but it's not. I mean, it's quite symmetric, everything. So if you look at not only the crater, but also how the dislocations below are and everything, it's kind of symmetric. There is no preference, right or left or up or down. That's in general. Just I could show a lot of pictures of this kind, but we didn't see any asymmetry in that sense.
Okay. Any more questions? Yes.
Small question. So let's say in practice, where do these high velocity impacts occur? In which application or in practice?
In the tokamaks, the plasma is hard to control. No? So sometimes we have these plasma disruptions. So the plasma touches the wall, erodes the material. So you have dust in the plasma. They call dust whatever is not helium or tritium or deuterium or the gas that you want to have there. So these dust particles are in the plasma for a short time or something, and then they go back to the wall at very high velocity.
Yeah, I missed that. Sorry.
Yeah, no, I probably didn't explain.
Yes.
So when this subject came up, I did some times ago something with beryllium, and there was always
Right.
that you did have this beryllium then on top of this tungsten, and you studied, in my case, then the interaction, whatever. But I mean, now you have only that from the tungsten point of view. Why is that?
As far as I know, they don't want to use beryllium anymore. Beryllium is very toxic and it's really bad. I mean, so for ITER, they will use only tungsten. And well, it's not perfect. It has also some drawbacks. But up to now, it's tungsten what we'll be using in ITER, and then after ITER, who knows? But yeah, beryllium, I think, is now out of the table.
Yes, yes.
So yeah, I come from a different field, condensed matter physics, and so I don't know much about this area, but I came because I think these kind of simulations are really cool. But so I kind of wanted to know, like, what's the overall, like, the kind of motivation for doing these kind of simulations? Is it the hopes to create better panels for like the tungsten the inside of the tokamaks, or to prevent these kind of
well, I mean, to prevent the impacts and everything, you have to maybe improve the way you control the plasma and everything, but then it seems that you will always have some kind of impacts like that, small particles going back to the wall, high velocity. So the point is to understand this, what will happen in the target, I mean, in the material properly. It's difficult to do the experiments. For example, in the experiments, they can only use particles about 15 microns in diameter. They cannot do smaller ones because it agglomerates and they cannot.
Is the experiment an actual tokamak functioning, or is it a separate experiment?
They use some kind of light gas gun, or there are other techniques as well. So the experiment is difficult, and then if you do the real tokamak, so if you analyze the results in the tokamak, you don't know much about the impact. You just can observe post-mortem the wall and see craters and everything there. So you don't know well what happened. Just you see craters and some imperfections and all that. So it was to understand better how is an impact from the atomistic point of view. You have a lot of information, and of course we are not in the same scale, but it looks like everything is kind of realistic.
Well, I have one question. Is like everything is going to be related to the dislocations patterns that you have below the impact. So somehow you have been able to say something about the patterns that are below, but I wonder. It seems that there is no. You say that this is not the area that covers the crater. It depends on other parameters, different things. Could you comment more on this kind of?
Yes, maybe what I meant that is maybe here. I mean, the ratio between the two projectiles here, one was 4 nanometers, the other is 8 nanometers diameter. So the area of this, the ratio between the two areas is 4. This is what I meant, the ratio between areas. So this is what we don't know yet, how it goes with the size. It seems that it's more or less parabolic with the kinetic energy and all that, but there is a lot of work to do here to analyze the dislocations, and also we don't have experiments to compare. So we have a lot of data, and we are analyzing the kind of dislocation and more, but we don't have experiments. For example,
I would say the dislocations are the ones that are like a long range breaking the materials, so to say. It's like, okay, I hit it, I made some crater, something around, but the real damage to the material is the dislocation pattern that you go in. Okay. And this is like trying to avoid that. I found it like very difficult, or something has or tungsten has to have some dopants or something like that, so that dislocations are pinned there and so on, but I don't know how this pinning will behave with these high energies when everything has like higher speeds and so on and so forth.
Right. So exactly. I mean, there are a lot of questions there to check. And for example, the effect of the temperature in the amount of dislocations that you have or the remain after the impact, it's quite significant. So this is something that we are now analyzing, and we are preparing the paper with
all these dislocation patterns compared to the grain size and so on, because I don't think these things will be done just as a single crystal. So.
No, of course. No, in the experiment you have a polycrystal, but they don't have analysis of the dislocations in the target.
So you have to start
something to do next. Also experimentally will be very nice.
Okay. So in this case, then there are no more questions. So questions. So then thank you very much for your talk, and let's thank the speaker again. We will be here in Friday. If you have any further questions, please contact me and I will pass it in YouTube. Okay, thank you.
I was really wondering why you have the same image when you have this polycrystalline and the other. It's not very difficult, but I mean, as he taught, you should have a completely different, let's say, pattern. I really find it was very similar from my point of view.
Yes.
So I would expect completely different things.
Yes, you see that as you have cracked, and it's almost the same shape.
Yes, exactly. So
it's well, okay.
I mean, when you have an experimentalist, so when you have a single crystal, it's like butter. I mean, you for example, if you have copper with your finger, you make a mark there. If you have a foil, a copper foil, it's not so easy to do that in tungsten. It's not as that. Tungsten is much harder than copper. I agree, but I mean, if you have dislocation, then in a single crystal, you put this dislocation, it goes through. But if you have already this dislocations, that it should work down much harder against any impact.
So you mean that this crater should be larger?
No, the other way around. I would say should be much smaller from simple point of view.
No, it's what we saw. You see, in this is below. So the single crystal is the blue square, and these polycrystals are here.
Okay. Yeah, I didn't pay too much attention to the curve yet.
But we don't know yet if this is really the case or can change if we do more simulations. Probably won't change that much if we repeat simulations, because crystals are big enough and everything. So I was thinking that the reason could be maybe here part of the energy is imparted in moving a little bit these nanocrystals instead of making the crater. So it can be, and then there is kind of change of trend or a threshold or something, and then when you have a lot of single crystals, I mean a lot of nanocrystals, then you are like a polycrystal.
It gets a mess. I mean,
so then it's even worse. I mean, you have bigger crater for these high velocities. So
the point is that you only not do that, but also he has plenty of knowledge on magnetisms and strongly correlated systems and things like that, because he has done experiments on strongly correlated systems. In fact, he has done some experimental lab work in the past. So he really knows what to look for. I was thinking like a candidate for this post that we have.
I understood. So
that he can start working in this European oxide, things like that. If you like it to do something. So because his expert on this kind of strongly correlated correlations and so on is really worthwhile to put it them also in the European compounds, these oxides.
Sounds okay.
Okay. So I hope you didn't find it boring.
No, I mean, as I told you, I did in the beginning some experiment for this beryllium and tungsten, the growth and how this grows. And the background always behind was why we are doing that, because they wanted to use that in this fusion physics. I'm not sure anymore why was the reason to use this beryllium, but it had some certain properties that the tungsten only did not have.
The beryllium was used in JET, in the tokamaks, this European facility in the UK. And I think it's good for the, because it's low zeta material, so you don't want to have in the plasma high zeta materials.
Yes,
and things like that. But it's very toxic, so it's really a mess to work in that environment. Didn't want to use.
It's a mess in everything.
But then I think that they came up also with to put carbon instead of.
I mean, we are of course studying pure tungsten because it's difficult to put more things. Put helium just to. But if you want to study some alloy, you need an interatomic potential that describes the alloy properly and not always easy. So.
Okay. Yeah. Thanks a lot.
Okay, thank you.
Thank you.
Yeah. So I switch off here. I leave this.
Sorry?
No, I leave this.
Yes, take out or delete the file.
I was supposed to read the email more carefully. I was supposed to read the email more carefully.
What?
Because coming here, I didn't know what it was talking about.
Okay.
And then I didn't catch it at the beginning.
What's about
the fusion reactor?
Fusion reactors, yes. The new material. Another fusion is again in a wave.
Yeah.
But in principle,
and you're planning to molecular dynamics in the project?
No. In principle, it's just to, well, I don't know what in principle, the idea is to start doing some basic electronic structural calculations. That's the deal to do the electronic structural calculation, because you have done something in the past concerning structural calculations, how to run VASP or similar codes. And of course, if we can do things like this will be wonderful. Much better than the planet thing, but
this is just something I did recently. So
just to show that